In mathematics, groups and coding theory is a very important topic. So today we start with the some topics from groups and coding theory. Now the first unit is integers. Now equivalence relation is nothing but a relation which is reflexive, symmetric and transitive relation on that set that we have seen already. Now see what is the meaning of equivalence class. When R is an equivalence relation on a set A, it is customary to write A, R, B instead of ordered pair A, B belonging to R. Also, since an equivalence relation is just a generalization of equality, we can write the symbols such as this one or this one or this one to denote the equivalence relation. Now, if this relation is an equivalence relation on a set A and A is a member of A, then the set equivalence class of A, it contains element X in A such that X is related to A. So this is called as the equivalence class of the set A containing A. So what is basically an equivalence class? Whenever some relation is an equivalence relation on set A, then for every element A from that set A, we can define equivalence class. So equivalence class of A contains all those elements X in A which are related to A. Now definitely this set is non-empty, as for every element A in A is related to A because the relation is reflexive. So every equivalence class is non-empty. Now see this example. Now see A equal to 1, 2, 3. R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. This is an equivalence relation on A. Now for every element of A, we decide the equivalence class. Now equivalence class of 1. Now by definition it contains X in A such that X is related to 1. Now by observing the pairs, here 1 is related to 1 and 2 is related to 1. So the elements 1 and 2 from A are related to 1. So what is equivalence class of 1? It is 1, 2. Similar way, what is equivalence class of 2? By definition, it contains X in A such that X is related to 2. So here 2 is related to 2 and 1 is related to 2. So again 2 and 1 means 1 and 2 are members of equivalence class of 2. Now equivalence class of 3. So it contains X in A such that X is related to 3. Now see which members of A are related to 3. It means 3 must be second element of every pair. So here 3 is related to 3. So no other element of A is related to 3. So equivalence class of 3 contains only element 3. So in this way, for every element of that set, we can decide its equivalence classes. Now here, if you observe, equivalence class of 1 and equivalence class of 2 are identical. That means they are exactly same. And equivalence class of 1 and equivalence class of 3 are disjoint, means they do not have any element common. Same way, equivalence class of 2 and equivalence class of 3, again they are disjoint. Now see one example. Let Z be the set of integers and n be a positive integer. If A, B belong to Z, define A related to B if A is congruent to B modulo n. That is, if n divides A minus B. So that this relation is an equivalence relation on Z. Determine the equivalence classes of Z. Now here first we have to show that the relation is an equivalence relation on Z. It means we have to show that it is reflexive, symmetric and transitive. So in all we require three elements of Z to prove these three properties. So let A, B, C belong to Z. Now first is reflexive. So we have to show that every element A in Z is related to itself. Now by definition, A will be related to A if A is congruent to A modulo N. That means N divides A minus A. Now N is a natural number. So N divides 0. That means N divides A minus A. So by definition of congruence, we get A is congruent to A modulo N. So by definition of relation, A is related to A, and this is true for all A belonging to Z. Hence, relation is reflexive. Now, second property is symmetry. Now, in symmetry, for two elements A and B in Z, we assume that A is related to B. In that case, we have to show B related to A. Now, as A is related to B, by definition, A is congruent to B modulo N. So again, by definition of congruence, this implies N divides A minus B. Now, by definition of divisibility, N divides A minus B implies A minus B is equal to N into K for some K belonging to Z. Now, from A related to B, we have to show B related to A. That means B is congruent to A modulo N. So, we consider B minus A. So, it is minus of A minus B, which is equal to minus of Nk. So, it is equal to N into minus K. As K is an integer, minus K is again an integer, so it is L. So, finally, we get B minus A is equal to N into L. Implies N divides B minus A by definition of divisibility. Again, by definition of congruence, N divides B minus A means B congruent to A modulo N. So, by using the definition of this relation, we get B related to A. Thus, A related to B implies B related to A. So, R is symmetry. Now, the third property is transitive. Now in transitivity, we assume that A related to B and B related to C. So by definition of relation, we get A is congruent to B modulo N and B is congruent to C modulo N. So by definition of congruence, N divides A minus B and N divides B minus C. So by definition of divisibility, A minus B equal to N into K1 and B minus C is equal to N into K2 for some K1, K2 belonging to Z. Now adding these two equations, we get A minus C is equal to A minus B plus B minus C, which is NK1 plus NK2. That means A minus C is equal to N into K1 plus K2, where K1 plus K2 is an integer. So by definition of divisibility, N divides A minus C. So by definition of congruence, A is congruent to C modulo N. So by definition of relation, A is related to C. So R is transitive. So we have shown that R is reflexive, symmetric and transitive. Hence, it is an equivalence relation on Z. Now the next part is to decide equivalence classes. So for any element A, by definition equivalence class of A is X in Z such that X is related to A. Now we simplify it further. So X related to A means X is congruent to A modulo N. It means it contains X in Z such that N divides X minus A by definition of congruence. It means it is X in Z such that X minus A is Nk for some K belonging to Z by definition of divisibility. Therefore, equivalence class of A contains X in Z such that X is A plus Nk for some K in Z. Thus, equivalence class of A is equal to A plus Nk, K belonging to Z. So, this is the general equivalence class of A for any A belonging to Z. Now, by taking particular values of N, we can find the equivalence classes. So, if I consider N is equal to 7 here, Then equivalence class of A will be A plus 7k, where k is an integer. Again, by taking particular values of A, we can find equivalence class of every element of Z. For example, if I take A equal to 1 here, then equivalence class of 1 will be 1 plus 7k, k in Z. Now as k is varying over set of integers, take k equal to 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on. So for k is 0, this will be 1 plus 7 into 0, which is 1. For k is 1, it is 1 plus 7 into 1, which is 8. Similar way, for k is equal to minus 1, 1 plus 7 into minus 1, which is 1 minus 7 equal to minus 6. So in this way we get equivalence class of 1. Similar way you can put a is 2, a is 3, a is minus 1, minus 2 and so on. Now equivalence class of A equal to x in Z such that x is congruent to A modulo n. It's called as the congruence class of A modulo n. This is also called as residue class of A modulo n.